Hi, I am Archit Jaiswal and I will be talking about VIPR tool. It's called Verification of IP Trust, and it's a framework that utilizes machine learning to detect Trojan circuitry in an IP design. So here it's basically a pseudo self-referencing tool where we don't have to have a golden design of the benchmark that we are trying to evaluate. So I will be using a UART 232 design, and here is my test design, which is a Verilog file. Here we can see it. It's a UART design, and this will be something we will be testing to this framework. Since this is a machine learning framework, we have to train it, and here is my training data set. So this UR232 has different variants. It's D1100, 1200, 1300, and till 1600. And all these different variants inside these folders, I have different Trojan inserted benchmarks. And here it says combination 3, so it's basically a combinational Trojan with 3 gates trigger. And here we can see there are different type of Trojans inserted, like Trojan examples in it. So we go inside this directory. Here is the Verilog file, and here is the labels file. This labels file is it has basically the information about which nets are free nets and which nets are Trojan nets. So here is the design that has all the wires defined here, and here in this file it's telling this net name means this wire, is it free or is it connected to a Trojan circuitry. So here at the end there are few wires that are connected to the Trojan circuitry. Here that says Trojan. So basically we already have the information on where we have inserted Trojan in this design, and we will be using this to train our machine learning model. So this is a supervised machine learning framework. So here I'll go back to my launcher code. Here we can see initially it's going to take this training data set, and it will have to extract the features that are relevant to this framework. So here it's going to go into each of these folders. It's going to extract all the features that are relevant to this framework from this Verilog design files, and it's going to use this labels to train itself. So I will go here and I will be launching the framework, and here I'm launching it. It's extracting the VIPR. Here it says extracting the VIPR features from the test design. So this is the test design, and here we can see initially it just had the Verilog file and the labels file, and now it has this .csv files that are made by the feature extraction code. And now it's labeling the test data. So it modified that label.csv file, and here it has started extracting the information from this training directory. So here we will see this training directory, and it will go inside one of these our T1400, and it's going to start creating multiple extraction CSV files. So I will have to kill this right now, because since we have so many benchmark designs here, I think it's about 600 files. I will kill this, and I will show you. So here we can see it has already started creating this extraction files. So this is basically showing that it's sequential Trojan with 4 trigger conditions, and it will going to go in all of these designs and extract the features that are basically that are basically the Trojans that are sequential Trojans that has four trigger number of trigger gates. So it's going to take quite a while, and just for the sake of time I am killing this. Now I already executed this code, and this pre-process training data is stored in another directory that's here. So here we can see it has basically extracted the features, and it has this combinational 3 trigger, then combinational 3 trigger quant train. So it's min max train, quant train, standard train. There are like different types of features that are relevant to different types of training models. So here we can see that's also for the sequential Trojans with different trigger condition 3, 4, 6, 7, all the way till 8. It depends on what type of Trojan data set we are giving. It could go more than 8. It just depends a lot on what data we are feeding in. So here I have this execution of the pre-processing. So I will now go ahead and comment the code that's performing processing, so we can save some time, and I will show you the execution of the machine learning model after it's done processing. So here I'm commenting out my code that was supposed to do the extraction on the training data, and I will go here and I will be launching the directory. I mean, I will be executing the framework on the directories that already has this extraction done. So here I launch it, and it was, as we can see, it went through really fast because it already found those files, and now it has already started using those training data, the extracted training data. So here we can see that total number of nets in the training data are close to 30,000, and the test data has 306 nets or wires, and the training data Trojan nets, I mean the training data set has this many 18,000 Trojan wires labeled, and the test data set Trojan nets are just 10. So it's going to now train the machine learning model based on this training and test data. So it's training this random forest classifier. Here it's done training, so we can see true positive, true negative, false positive, false negative, and here it has KNN, here it has Gaussian naive Bayes, and it's now training support vector machine. This model specifically takes quite a long time, so I will be pausing the video and then playing it once this model is done. Right, now the training support vector machine is done. So here we can see the results: 9 true positive, 22 false positive, and 274 false negative, 1 false true negative, and 1 false negative. So here we have implemented a voting scheme where it's going to see how many models have voted for wire being safe. If the majority of vote goes to the wire being safe, then it's going to label it as SafeNet, and if multiple models says it's TrojanNet, then it's going to label it as TrojanNet. So even after we are done voting, we still do post-processing, and in this post-processing step we further improve the accuracy of this by reducing this false positives and false negatives. So here we have this level 1 post-processing that's described, and Then we have this level 2 post-processing, and after that we get the final result that has this breakdown of how we made improvements on true positive, and here we can see that it is also describing what net it found that has Trojan circuitry connected to it. So we performed the threshold filtering where we see what was the toggle rate and many other things that are described in the paper. So here, after that processing is done, we get a final breakdown of what were the outcomes. So we have this 3 levels of processing: level 1, level 2, and level 3. And after the final post-processing, we can see that the false positives went down from 22 to 3, and the false negatives, in this case it actually went to from 1 to 4, but it depends a lot on how we are tuning the parameters of this machine learning model. So we can go in the code and we can change different parameters. We can do the hyperparameter tuning, and based on that it's going to give us different sets of results, and it also depends a lot on what training data are we feeding in. So here we have this KNN neighbor, that's a parameter, and here we have different we can put different weights here while training. So based on all this changes, we can further improve the detection accuracy. So here we get the final results, and the final results are also stored into a CSV file for further analysis. So here we can see it created this directory, and inside here we have this different CSV files, this log files, and it also has this graph. So it's basically showing what were the Trojan nets that we found and where they're connected to, what gates they're connected to, things like that. So yeah, that was a quick overview of how this tool works, and I hope it was informative. Thank you so much.